Evening to you all. I am Dr. Anbuchayan, Associate Professor in the Department of Physics, Srm Vec Engineering College, and one of the coordinator of this today event. So the important event, the guest lecture on nano dimensional films and basics and applications. I welcome our principal, beloved principal and vice principal sir, and head of the department physics and head of the various departments and faculty members of our college and also from other colleges and student of our college and also other college students and research scholars of various institution and also in our institution. I welcome you all. And today the guest speaker is, I welcome the speaker, Dr. Paul Joseph, Assistant Professor, Department of Physics, National Institute of Technology, Warangal, Telangana. And our speaker is the area of nanomaterial. So the uh, is doing research in the field of dilute magnetic material, specific area of interest, transporting conducting oxide thin film, electrochromic thin film, electro dye-sensitive solar cell, polymer solar cell, and fabrication of thin film using PLD and thermal technique, device fabrication using raised film. And uh, our speaker, today's speaker, he did UG from St. Joseph College of Arts and Science, Kadalur, completed PG from Loyola College, Chennai, and completed MPhil PhD from University of Madras, and also sir did a B.Ed from the College of Education, Saidapet, Chennai. And also he did a postdoctoral from National University of Taiwan, and he is a member of professional societies, various societies, Material Research Society of India, Magnetic Society of India, life member, and IEEE, Indian Physics Association. And now presently, Sir is guiding the research scholars and also completed the project. One project is completed, one project is going on around the sanctioned amount of 26 lakhs. And so our speaker is the area of interest is nanotechnology. Definitely, you can have this type of speaker for updating the knowledge of nanotechnology. Nowadays, you know the importance of nanotechnology. So we are the Department of Physics regularly arranging this type of seminar, sir. For this is the second seminar for this semester. In our department, 10 faculty member and 5 faculty members are PhD, and 3 faculty members are now doing PhD in affiliated to Anna University and University of Madras. And so our regularly we are arranging the seminar semester for every semester 5 guest lectures, sir, every year. And this is a second guest lecture, sir. So I welcome the speaker. Now I hand over the session to the speaker. Before hand over the session, I request all the participants to mute your mic. And if we have now the speaker is presenting the topic about the nano dimensional material. You know the nanotechnology is important nowadays to design characterization of the material at the nanoscale. So what is the quantum effect on the nanoscale? We will discuss all this information in this guest lecture. And if you have any doubt, any queries, you can discuss with our speaker after the completion of this lecture. Now, I heartily welcome our today's speaker, Dr. Paul Joseph, sir, Assistant Professor, Department of Physics, NIT Warangal. Thank you, all the participants, sir. Thank you, sir. Now the session. Yes.
So thank you very much for your nice introduction. And also I thank the organizers for giving me this opportunity. Also I thank all the participants for sparing their time to listen to my lecture. So I have shared my screen, sir. Is it visible, sir?
Yeah, visible, sir. Yeah, yes, visible, sir.
Right.
Visible and audible, sir. Visible and
right.
audible.
Right, sir. Thank you. So now, let us start the lecture. So the title of my presentation is Nano-Dimensional Films from Basics to Applications. Okay, so that's the title. So the reason for choosing this particular title is because sir requested to discuss on nanomaterials. So I thought that instead of going for nano powders, which is very common, and also you find it in many of the textbooks, even in the curriculum of several of the institutions. So whereas nano-dimensional films, which are also having a dimension of the order of a few 10 to few hundreds of nanometers, and what is the mechanism behind the formation of these films, and how to characterize these films are not that much dealt in detail in several of the curriculum in Indian context, and also several of the gadgets which we are using in our day-to-day life has a lot number of relevance to these thin films. Okay, so in the due course of this lecture, you'll try to understand that one, and I'll try to scale down the lecture wherever it's possible for the benefit of students. Also, I'll try to outline some of the research-oriented aspects for the benefit of the faculty who are doing their PhD. So the outline of my talk is like this. First, I will give an introduction, something like an overview of a nano dimension. First, I will deal with what is a thin films, and then in between, I will also give an overview of a nano dimension, where it is appearing, and what is a limit for this thin film. And next, I will go for basics of thin film. So how is it formed, and then how we can characterize some of the basic characterization which is necessary to characterize the quality of the film. And next one, I will be focusing on alternative transparent conducting electrodes. So this will be essentially a thin films. So why I want to discuss on this particular material or this particular application, and I will introduce some of the basics of transparent conducting electrodes. In short, we can call it as the TCE, or sometimes they also call it as TCOs if it is an oxide system. Okay, and next one I will try to discuss on spray deposited tantalum doped tin oxide transparent conducting oxide thin film, and I will discuss some of the results of its characterization. Also, I will try to discuss some application based on this particular thin film. Okay, so in the first part of the my talk, I will try to give a lot of basics on thin films, and in the second part, I will give on the application. And I will focus more on the first part than on the second part, because that will be benefiting for the students. And then finally, I will conclude. Okay. So now coming to the introduction of this particular lecture, you will see that today's life is very strongly influenced by thin films. So especially based on applications. Especially if you see in this pandemic situation, all of us are separated from each of us, and we are bound to do several things through online only. And in this context, you will see that several people are using tabs or mobile phones or touchscreen based devices. So there is a huge increase in the usage of such kind of devices. And essentially, you will see this, all these gadgets will be using several materials in its thin film form, because present day technology is much more towards the compact devices. So we always want a slim device for our use, so that the weight will be very less and it will be stylish also several times. Okay, so in this aspect we will see that why thin film is very important, and we can see some of the examples which are shown here. We can see that several of the spectacles which we are using, which comes with thin film coating. We may not be aware of that one, but most of us will be using this one. Okay, so there will be an anti-glare coating on the surface of the spectacles. Also, in an expensive cameras, also you can see some kind of coatings will be there on the surface of the lens. So likewise, when you use a mobile phone, also you will see that apart from the scratch-proof card, you will see that at the base of this one there will be a touch screen. Essentially, this touch screen, whenever you are using, that carries information for you to attend a call or to see a movie played in this particular screen. So always when you touch it, you are giving a signal. So how this signal is carried actually? So almost the surface of your mobile phone looks like a glass. So glass, you know that it is an insulator, but how come it is carrying? So essentially, you will see that a lot number of thin layers are coated on the device, on the display device of your mobile phone or touchscreen laptops. So likewise, when you come to OLEDs, also you have a lot of transparent conducting electrode thin films are used up. or even when you take a SIM card, you will see that there is a thin gold layer which is coated there. Okay, so we cannot use a thick gold layer because it's going to be very expensive. So people use actually a very thin layer of gold because gold is a noble material and it has very good corrosion resistance and all, and also very good electrical conductivity. So that's why almost all your SIM cards will carry a very thin layer of gold. Not only your SIM cards, several of your electronic devices inside your hardware will also have small amount of gold. Okay, but everything will be in the form of a thin film. So these are some of the applications. So likewise, even if you have a packet of chips from a very good company, you will see that the interior of this one will have a thin or sometimes even a thick coating of aluminum foil. Okay, so this will be integrated to your polymeric sheet. So because this will give you a very good shelf life for the product which you are packing inside and keeps the food very much fresh for quite long time. Okay, so these are all some of the applications. And recently, you will see that several people, several companies have marketed, a jerkin or shirts with very thin solar cell integrated into your overcoat. So that means it should be a flexible one. So obviously, it should be very thin so that you can wear that one. And when you are going on a bike, automatically these flexible solar cells on your surface of your wearable coats will gather the power, and then they will be helpful to charge your mobile phone or something like that. Okay, so this is some of the very limited application which I have focused. In fact, a lot number of applications are there for thin films. So it becomes very essential for us to understand what is a thin film and how to prepare a thin film and how to characterize a thin film for various applications. Okay, so this lecture may not be sufficient enough to explain all those things, but anyhow, maximum possible thing we'll try to discuss on for thin films. So now coming to the very fundamental thing, you can see that what is a thin film? So by definition, thin films are thin layer of material, so less than about 1 micrometer, which are deposited over another material that is called as a substrate. So obviously, it means that thin films are not freestanding. Okay, so in general, thin films should have a substrate over which you have to deposit a material, and a thickness for which the property of the film asymptotically reaches that of the bulk is reasonably characterized as thick. So when I say a thin film, so obviously a thickness factor is coming into picture. So we have to question how thick is the film. That is very, very important. Okay? So by definition, we are telling that it's about 1 micrometer. But for depending upon application and material, you will see that the definition may actually change, or the application may change, starting from few tens of nanometer up to even few hundreds of nanometer. So that is the limit. So we can see that films typically used in applications range from few atoms. So few monolayers of films are also possible to make up to 0.00 micrometer also, or even up to 1 micrometer thick. So how to define the limit? So it means that any film which is made in a nano-dimensional form of the order of 10 power minus 9 nanometer, okay, its property should be very much different from that of the bulk. So that limit below the thickness which your property of a material changes from its bulk counterpart, will be called as a thin film limit. Okay, and also it depends upon application, and the thickness may vary from material to material. So this is the picture which shows that particular thin film. So this green color part is actually a substrate. It may be a glass or it may be a polymeric sheet kind of things. Okay, it depends upon application. And then on the top, you are going to have a red color region which is called as a thin film. So essentially, your thin film will be a two-dimensional material. Okay, so which means that you will have an X and Y, which will have a larger area. And essentially, when you come to your thickness of the film, it will be very, very low. So that's why we are not going to consider this thickness of this film very explicitly. So it's called as a two-dimensional material, because the thickness most of the time will be very, very, very thin, and its property will be different from the bulk counterpart. So that's why we call it as a two-dimensional material. So if you see that this film, this picture which shows you the comparison, say for example, 1 millimeter is called as a sheet or plate. When it comes to 10 micrometer, we can call it as a thick film. And then around 10,000 angstrom or 1 micron, we can call it as a foil. Okay, so we can call it as a foil. Foil means it's easily, you can handle it very easily. And up to this point, you don't need any substrate for the material to be stable. So you can roll it, you can handle it easily. But below this limit of 1 micrometer, except for graphene is a special case. Okay, graphene can be an isolated thin film without a substrate also. But to put it into application, obviously you need a substrate so that you can handle it and you can preserve it properly. But below this 1 micrometer limit, you will see that, say, if it is 1,000 angstrom or 100 angstrom or even 10 angstrom, it cannot be a freestanding material. It always needs the support of a material which is called as a substrate. Okay, so this is the definition of thin film. And what are the applications? I mean, what are the advantages of a thin film? Thin films are very much compact. They have better performance, better reliability, relatively low cost of production. Depending upon the material, it will be there. Okay, so this has to be understood in terms of application. For example, in your SIM card, I cannot have 2 mm thick gold. That means your SIM card becomes expensive, and people will try to pickpocket your SIM card also. So you have to have a low cost of production. So I should have a very thin layer of gold, but still it will serve our purpose. So that's in that manner it's called as a low cost of production, and obviously low package of it, because the thickness of the material in several aspects are going to be scaled down. So the whole device will be looking very lightweight. Okay. Now coming to how to form thin films. Okay. So can I melt it and cast it, or I should make it into a layer by layer? So several questions will come into our mind how we can make a thin film. Okay. So there are 3 basic steps to form a thin film by physical vapor deposition called as PVD or chemical vapor deposition called as CVD. So the very fundamental thing is you have to create the material in vapor form, and then you have to transport the material from the source towards the substrate, and then the film has to grow. Okay, so why we have to create the material in the sense we will have a bulk material in our hand, so we have to create a vapors by heating this particular material, and these vapors will be created, and these vapors has to be reformed onto a substrate to a thickness up to which we need for our application. So that's why we have to create a vapor, transport it effectively towards a substrate, it may be a glass or something like that, and then try to grow with a particular thickness and also a particular property of your interest. And then this film has to grow onto the substrate. So these 3 things are the fundamental. Creation of the material in vapor form. It can be a chemical method or a physical method, whatever it is. And then you have to effectively transport that particular created vapors to the substrate, and then you have to reform that particular material onto the substrate. So some of the steps which are shown here are for film formation. First one is arrival of a single atom, because the moment when I evaporate it, immediately my surface will not be covered to form a thin film. That will not happen. So it grows slowly. So initially when I evaporate the species and the atoms will be coming to the substrate, you will see that onto the substrate only few atoms will be sitting here and there. Okay, and there won't be a continuity between one atom or set of molecules there. So there will be substrates visible there. So this yellow color thing is actually a substrate, and this is actually the atom which is coming there, atom or molecule, whatever it is. Okay, so now this will be growing into a doublet. They will merge with each other with more number of incoming atoms or molecules. At the same time, the substrate has to be heated. Most of the time, the substrate will be given a temperature called as a substrate temperature. So the substrate temperature will increase the kinetic energy of these atoms or molecules, help them to move from one location to another location, and then it will help them to form a doublet, and then it will grow in size. It is called as a nucleation, and then this nucleation will further grow in size, and that is called as growth. And these islands, independent islands which are grown here, will try to merge with each other. That is called as coalescence, or merging with each other. Several of such islands will be merging with each other, and with respect to time, after say half an hour or 1 hour, you will see that the entire yellow colored substrate will be covered with this orange color material as a 2-dimensional layer. Okay, so this is called as surface coverage. If you have some uncoated area here, and then these things are called as pinholes. If you have an yellow color here, for example, okay, that is called as a pinhole. That means your film is not of good quality. Some exposed substrates, uncoated area are going to be seen. This is the fundamental steps in formation of thin film. then coming to the atomistic processes which can happen during thin film growth. So when I am going to use a physical vapor deposition method or a chemical vapor deposition method, the moment I evaporate, there is no guarantee that these evaporated species should go and sit on the substrate. No guarantee. Because depending upon the distance and depending upon the kinetic energy of the vapors which are coming, several processes can happen in this system. Say, for example, you can have an adsorbed species. The species which is evaporated may just sit on the substrate without a chemical bonding or a proper physical bonding to the substrate. Or it can simply condense into small particles like a globules. That's called as condensation. Or if the temperature of your substrate is very high, you will see that the species which is settling on your substrate sees a higher temperature. Once again, it can re-evaporate out of the system. Or if it has a stable conditions or an optimal conditions, you will see that these adsorbed species will nucleate with each other and then they can try to grow. Or otherwise, you will see that this deposited material can penetrate into your substrate, or sometimes after a particular growth of your material, you will see that the substrate species can also penetrate into your thin film. So this is called as interdiffusion. So all these phenomena can happen during the formation of a thin film. So some may be beneficial, some may not be beneficial. So we have to see which are all beneficial for making a film formation. So as long as adsorption is concerned, it may not be that much beneficial process, because once adsorption is going to happen in a bigger way, you will see that it will not be having a proper bonding. It looks like a film. Later, when you wipe it off, it comes out of the substrate. So condensation, to some extent, it is okay. Re-evaporation, definitely not necessary. And interdiffusion is also most of the time not necessary unless you want to dope it into the substrate. Okay, that is not necessary. So most of the time you will see that a kind of diffusion along the surface, okay, and then a kind of nucleation and then further growth is actually necessary to have a film of sufficient thickness for our application. Okay, so when you are going to adapt a particular technique like PVD or CVD, you have to understand what is the principle behind that particular technique. And then you have to see what are all the atomic processes that will happen dominantly, and you have to adjust your substrate temperature, distance, and the evaporation rate, all those things, such that your nucleation should be dominated, re-evaporation and all should be minimized. Okay, you have to fix the substrate temperature accordingly. So now coming to the cross-sectional view of thin film formation, there may be different kinds of thin film formation stages. So we are just we are seeing here the cross section of the film. So you can see here initial stages when you are having a nucleation. This is the substrate. Okay, the striped line is a substrate. You will see that these are all the species which are coming to the substrate. So now if you see here, there are a lot of gaps in between the molecules or atoms here. That means it is just in the process of facing the surface of the substrate. So just nucleation takes place here. You are seeing that several of the atoms are forming small islands or group. Okay, and some places are not even covered. Now only the atoms or molecules are coming towards your substrate. Okay, so after coming here, it forms a nucleation, and with respect to more amount of species coming into the substrate, you will see that they grow in size, and then that is called as island growth. You see here, one bigger island is seen here, and much more islands are also seen here. And you can see that still there are some places which are not even covered by the species which you want to grow onto the substrate. So then the first part is called as coalescence. Once you keep on growing, you keep on depositing the material, you will see that these particular islands are trying to merge with each other. That's called as coalescence stage 1. And still there are some gaps are between the islands. And with respect to more time and more incoming flux of the evaporated species, you will see that this is called as coalescence stage 2. So here you will see that these islands are growing in much more bigger size, and almost they are covering the surface of the substrate, but still you are seeing some small gaps between the islands here. So it looks like a channel in the cross-sectional view. So it's called as a channel growth. Okay, and still with further deposition of the species, you will see that these channels will also be filled up with the material of your interest, and finally you are having a film grown onto the substrate. Okay, so this is actually called as a thickness T of your particular thin film. Okay, so now what we can do is we can classify the growth of this thin film into three major types. So first one is called as island growth mode, or it's also called as Walmer-Weber growth mode. So here in Walmer-Weber growth mode, you will see that you are going to have formation of islands here. Okay, formation of islands will be here. So it will form individual islands. These individual islands will grow in size and merge with each other. Okay, that is called as island growth mode or Walmer-Weber growth. And next one is layer by layer growth mode or Frank Vander Merwe growth mode. Here you will see that the films is grown as a layer by layer fashion. So here in island growth mode, you are seeing a lot of gaps. Before the gaps are filled up, islands are formed. So some uncovered substrate is seen here. Whereas in the case of Frank Vander Merwe growth mode, you will see that the entire substrate surface is covered first of all. Then only second layer will be grown. Okay, so this is called as layer by layer growth mode. So this layer by layer growth mode happens only in very sophisticated techniques like molecular beam epitaxial growth most of the time. And then sometimes if you control the rate of growth, it can also happen in some other techniques like PLD and also in the case of sputtering. But this is mostly favorable in the case of MBE techniques only. And next one is called as mixed growth mode or Stansky-Krasnov growth mode. Here you can see that both these techniques are going to happen there. Initially, it will be having a kind of layer by layer growth mode. As time proceeds, you will see that they form islands here and then they will be proceeding. Okay, so most of the time, this layer by layer growth mode gives a very good quality thin film. Whereas this island growth mode is not going to give you a very good quality thin film most of the time. Okay, and finally, this will be having a quality in between this. That's called as mixed growth or Stansky-Krasnov growth mode. Okay, so this is about the growth mode. So you have to see. Again, remember that when I just take an MBE, automatically layer by layer growth mode will not happen. You have to fix the deposition condition very precisely and monitor that one very carefully so that this growth will take place. Otherwise, eventually it will be ending up in mixed growth mode or island growth mode until you are going to monitor and precisely follow that particular deposition conditions. So that is very, very important. And then coming to the general factors that influence the growth of film and also quality of the film, that is important. Okay, so these are all these are all some of the essential factors which I have listed here, and this is mostly common for all kind of thin films. Okay, so cleanliness of the substrate is very important. Also, cleanliness of the deposition chamber is very, very, very important. Okay, so cleanliness is very important because if I have a substrate here, if I want to grow a thin film onto this one, suppose some kind of dust particle is sitting here, bigger dust particle, and if I grow a film like this, okay, and then you will see that this dust particle sitting here will be kind of inclusion there. So your film will not have a good lattice matching here, or some third element or foreign species will be sitting on the surface. Say for example, oil in your hand or sweat in your hand. If you are not handling the substrate properly, that will be a bigger problem for your device. Because we are speaking about thickness of the order of few tens to hundreds of nanometer. So in that regime, even a small dust particle sitting there will have a major influence on the properties of your thin film. The film itself may not form sometimes if it is going to be not clean. Okay, so this cleanliness is very, very important. Even if I purchase a substrate from a company, I just open the box and then I start depositing, it is not a clean one. Okay, because every second you will see that a lot of dust particles and the carbon from atmosphere are keep on depositing on your substrate. So every time you have to clean the substrate ultrasonically, immediately load it into the chamber and start your deposition to minimize the surface contamination. Okay, likewise, your deposition chamber also should be very, very clean. Suppose today I am using a low melting point material to be deposited. If I don't clean the inside of my chamber properly, tomorrow somebody is coming and using a high deposition, high vaporization point material. Say for example, if they are going to keep their substrate temperature around 800 degrees centigrade, then what will happen is yesterday's material which was deposited, we will see a high temperature in that region, and then it will start evaporating once again from the walls of the chamber sometimes, or from near the place where you are keeping your substrate, and then they will go and contaminate your substrate. Okay. So if I want a material X to be deposited onto my substrate, only X should be there. Some Y should not be there in my material. Okay, that is the very, very important thing. So very fundamental for any film deposition. And next one is type of substrate. So what kind of substrate I'm going to use? Okay, that is also very, very important. If I'm going to use a glass, that is one kind of deposition. If I use a polymer, then that is another kind of deposition. And what will be the crystalline quality of the film which is deposited on the surface? That is very, very important. If it is a cubic material, which I want to grow there, if I take the substrate also in the same cubic material, then the crystallographic properties will be very good. Because the deposited material will try to follow or replicate the same crystal structure which is in the substrate. That is very, very important. Likewise, the substrate temperature will also tell you what is the maximum limit for deposition of the substrate temperature. That is also very important. By keeping a polymeric sheet, I cannot go more than maximum 140 degrees centigrade. If I go more than 140 degrees centigrade, my polymer will be melted and it will evaporate, it will contaminate your chamber. So in case of polymeric materials, mostly several people don't give a substrate temperature, or they keep it very low, like 75 degrees centigrade to 100 degrees centigrade. If it is glass, we can go up to something like 400 degrees centigrade, depending upon the substrate. If it is a quartz, we can conveniently go up to 800 to 900 degrees centigrade. That is very important. So this type of substrate also dictates you what is a lattice match. Okay, so lattice matching is what I told you, this cubic structure of your material matching with the crystallographic structure of your substrate. That is called as epitaxial. Epi means, epitaxial means same kind of structure for your material and the substrate. Okay, or if you're not having a good quality substrate, you will see that instead of following the same crystallographic type, it will end up in a different crystallographic type, or into different orientations of the grain. That is called as polycrystalline. So the structured growth is in between these two. I will discuss in the due course. So substrate temperature is also important, as I told you, for glass or polymer. Then what kind of atmosphere you are going to give? Okay, that is also very, very important. I can use inert atmosphere by putting I can put an helium gas inside, or sometimes I can put a krypton gas inside, or I can use oxygen also. Depending upon what is your material, I have to choose this particular atmosphere, because this will help me to have a reaction during formation of the film, or it will help me to reduce or to modify the kinetic energy of the evaporated species to control the rate of deposition of film growth. Okay, and then film adherence. Adherence is very, very important. After deposition, if I wipe it off, it should not come out. Okay, that means the film is not formed; just it has absorbed on the surface. So likewise, rate of deposition is also very, very important. If the rate is very, very high, you will see that most of the time you will end up with the inferior quality thin film. So something like island growth mode or mixed growth mode, you will be ending up. If I want to have a layer by layer growth mode, to have an epitaxial film growth, I have to keep my rate of deposition very slow. But of course, it takes long time to deposit. But if you want to have a quality thin film, your rate of deposition should be very low. Okay, that is very, very important. And then coming to the cleaning process, how to clean the substrate. So first of all, you should decide what is a substrate, whether it is a glass or whether it is a polymer. Okay, so if it is a polymeric material, if I use strong acids, the substrate will be dissolved out. Okay, that should not happen. Or if I have a glass substrate, once again, I should not use a very much corrosive substrate. If I use a very much corrosive substrate, the surface will be etched out, and then the growth of the film may not happen properly. So the substrate cleaning is not universal. You have to clean, but what are the steps to use for cleaning will vary depending upon what is your material or what is your substrate, all those things. So for now, I have given some set of procedure to clean that one. So you can see here, first I can take my glass substrate, put it in an ultrasonicator, okay, in a proper solvent in a container. That is very important, because why I have to use an ultrasonicator means ultrasonicators will have frequency of the order of 20 kilohertz, right? So when they have 20 kilohertz frequency, you will see that at the bottom you will have a PZT crystal. Piezoelectric crystal will be there at the bottom. So when I'm going to oscillate this piezoelectric crystal at a very higher frequency in the range of ultrasound waves, you will see that inside this beaker where I have put my substrate along with a solvent, I cannot put it empty. I have to put some solvent here. So it will be creating bubbles. It will be creating lot number of bubbles at a rapid rate. Okay, of the order of ultrasonic frequency, it will create. So the moment it creates a lot of minute bubbles and cracks them immediately, you will see that a lot of kinetic energy and temperature local temperature will be seen there. A high temperature for a very fraction of a second will be developed on the surface of the substrate. So any dust particles sitting on the crevices or at the edges of the substrate will be removed off to a greater extent. That's why we are using ultrasonic cleaning. And then I can use it in a solvent or water, whatever it is. So first, generally what we'll do is we'll use a water first of all. Then you use a mild detergent. You should not put a strong detergent. Okay, just for namesake, I will put it as a Dettol. You should not put Dettol on all because it's a very strong one. Okay, it will etch off your substrate surface. So a lot of mild detergents are available in the market. You have to get that one and clean that one. Once again, you have to clean the soap solution with proper water. Otherwise, the soap solution itself will contaminate your substrate. And then put an isopropyl alcohol, and then DI water, and then acetone. Or I can even put acetone first, and then I can go for IPA. So you have to choose the material and then the solvent. And after doing this cleaning, we should go for plasma cleaning. So in plasma cleaning also, you will have a gaseous medium with positive and negative charges, and it will also clean the surface of your substrate effectively. I can do an ex situ cleaning with plasma, or I can load this substrate, clean the substrate inside a chamber. Inside the chamber also several times, some plasma setup will be there. There I can pass a gas like nitrogen or oxygen depending upon my necessity. I can apply a potential difference between two electrodes, and then you will see that these nitrogen and oxygen will have a gas discharge that will have a lot of positive and negative charges. They will be helping to clean the surface of my substrate. Okay, so this is a general substrate cleaning procedure. So once you have cleaned the substrate, assume that you have coated a film. Now we have to characterize the quality of the film. That is very important. So when you try to characterize the quality of the film, first one is tape test, whether the adherence is good or not. How to know that adherence is good or not? Okay, so what we can do is the simplest one is tape test. What you can do is you can take a scotch tape, white color tape, paste it on the coated area, remove it off. Suppose if the coating is coming off, so this is the coating, the edge is broken and it comes off with the tape, that means generally the adherence is not very good. Okay, so again, this is a qualitative test only. You can make it semi-quantitative. What we can do is you can take a diamond tip pen, and then you can make some lines, horizontal and vertical lines onto the film surface. This is just to test the film quality. Okay, so once you do a cross cut like this, after making a cross cut, once again you paste the tape on the surface of your substrate and peel it off. So suppose after peeling it off, say for example here, say 1, 2, 3, 4, 5, some almost like 4 to 5 squares are removed. Means adherence is somewhat good. Suppose in another film, several of the squares are removed here, means then the adherence is not very good. So this is also not very quantitative, it's semi-quantitative. So depending upon how many number of squares are coming out or not coming out, we can tell to greater extent quality of the adherence. Okay, this is only, again remember that this is a qualitative test because it depends upon what is the adhesive property of this tape and how fast you are pulling it. This is only a crude way of testing that. Okay, so apart from this cross-cut test, we can do a lot of mechanical tests like friction, wear, ductility, hardness. So many things are there. Using a nano indenter or nano tribometer, we can do that. Okay. Likewise, I can also do a scratch test. Okay, I can put a sharp tip on the surface. I can make a scratch. If it is scratching very easily, then the adherence is not going to be good. So I can test the adhesion strength by using a scratch test also. So all these things are already available in a nano indentation test. Okay, that is already available. And next one is very important parameter called as thickness, because the thickness of the film will tell you whether it is a thin film or a thick film. Okay, so obviously I have to study the film of the thickness of the film, because this film thickness will determine the property of your material. If it is an electrical material or if it is an optical material, thickness dependency is very much important. So I have to measure the thickness of my film very accurately. So what we can do is the simplest one is called as a surface stylus profiler. Okay, it's called as a stylus profiler. So what it will do is it will have a cantilever. It will have a sharp tip like this. Okay, it will have a cantilever. I can scribe this cantilever on the surface of the step edge. So what I have to do here is, I think it will be having a clear picture here. So now you see here in this picture which is shown here, this may be the substrate. This is a substrate here. over the substrate. Before coating the film, what I will do is I will keep a tape here. This red color thing is a tape. Okay, that means this is a substrate, and next one is I will put a tape onto the substrate here. I will paste it properly, or I can use a sharp knife edge kind of blade. I can keep it there. Okay, now it is not coated. Now what you do, you evaporate the material and coat this substrate here. So now coating will happen here and also here on the substrate surface of your tape. After coating is done, you remove the tape or knife edge. So ultimately your film will look like this. Okay, your film will be here and this will be uncoated area. So there is a step seen there like this. Okay, uncoated area, uncoated area. You are going to have a step that is called as a step edge. So if you want to use a stylus profiler, you are supposed to coat the material with this step edge only. And then I can put a stylus with a sharp tip like this, scribing from the substrate. And then when it comes here, it looks like a step. So this tip will climb over this one because it's a cantilever, it can move freely. So it will climb over the step. So I can use some software and then I can, make this as a flat one. And then I can take the difference between these two. By using a laser measurement techniques, precisely I can measure how much this cantilever has moved up. The difference will give me the thickness here. So this is a photograph of the equipment. I can see here this is a uncoated area, this is a coated area of a film. Okay, so after you scribe this one from here, it climbs there, and that is what is shown here as a step here. Okay, this is what is shown as a step here. So this part is actually the film thickness. So here I have measured it to be around 96 nanometer. So this is for yttrium barium copper oxide sample. So this is what is there. You can see some spikes here. So these spikes are noise sometimes. Suppose if your surface is not clean, say you stored the sample for quite long time, some small particles or paper particles of your tissue paper, something may be sitting there. So you have to clean surface first before making the measurement. You can use a inert gas atmosphere, clean the surface, then do it, so that you can you can omit these kind of avoid this kind of artifacts there. So this is basically the step edge. So that will give you the film thickness. And remember that because I'm scribing with a sharp tip, this may not be suitable for a soft material because it will go damage the material itself and you cannot estimate the accurate thickness. So the stylus profiler is suitable for hard materials, not for biological and very soft materials. Okay. Then coming to the X-ray diffraction, you assume that you measured the thickness. Now we have to study the crystalline quality of my material. So how to do the crystalline quality? Obviously, you know that you can use a X-ray diffraction using Bragg's law. So 2d sin theta will be equal to n times lambda, and you will assume the material as a periodic lattice. If you have a periodic lattice like this, and then an incoming X-ray radiation after reflected back will have a periodic interference pattern. It will have a maxima and minima, and that is what is shown here. So as an example, I am showing it for nickel oxide. Nickel oxide is a cubic system. So this is a standard database. So for any material which people are identifying, they will be depositing that one with a database called as JCPDS, Joint Committee on Powder Diffraction Standards. Okay, so this is the one. You can see that number is given there. This is a unique number for this particular material. Okay, so later if somebody is proving this is wrong, again it will come with another number. Okay, so now here in this number from this polycrystalline material, you see that some of the peaks are there. The blue color lines are actually the maxima, diffraction maxima. All other here are actually minima. So this is the line, position and intensity which I am supposed to compare with my film. So if I make a thin film, not necessarily the same diffraction lines which is seen in the diffraction pattern of the powder material should match. So this is very, very important. That is what is called as textured growth. Okay, or to calculate textured growth, we use a formula called as texture coefficient formula. So this texture coefficient formula will involve the intensity from the pattern onto our material, okay, our film. So now this is a standard material. This is my film, which I have deposited using a spray paralysis technique. Now, if same cubic structure is found in my material, how to identify that one? So I have to take a pattern for my different films here, and then I have to identify the location of my 2 theta here, and then the intensity, and then I have to compare whether this position and intensity are matching here. Okay, so but you see here in this nickel oxide pattern, which I have deposited here, in this standard pattern, you will see that the highest intensity peak is around 43 degree, 43.2 degree, 100%. So this is the 100% peak. Okay, whereas this is the second intensity peak, higher intensity peak. Then this is the third one, but the intensities are not matching. You see here in my pattern for thin films, the first 37.2 degree thin film peak is higher, whereas the actual 100 intensity peak is lesser. Okay, so this doesn't mean that the compound has not formed in my substrate. That's why thin film diffraction patterns are sometimes, little bit tricky. What will happen here is, if I have a diffraction pattern, say for example, if I have particles sitting in all possible orientations, HKL planes, then when I do a diffraction pattern, this kind of pattern will come. But because of the growth procedure which is happening in this material, you will see that all the particles will not have a random orientation. They have some kind of preferred orientation in only one direction or two direction only. They may be sitting like this uniformly, and the thickness is very, very thin. So once when the X-ray comes inside, even though you give a rotation for the substrate and you try to maximize the exposure, you will see that some other orientation will have higher intensity. So the intensities of the standard pattern will not match for your film most of the time. So you have to identify this is textured growth. So use this formula and plot that particular formula as a function of your variation, whether it's a concentration variation, whatever it is. If your texture coefficient value is less than 1, then it is a polycrystalline material. There is no preferred orientation. Suppose if your texture growth is more than 1, okay, it's like 1.4 or 2 or 3, then it is a textured growth. So this is very important for thin films. Most of the time, thin film patterns, unless it is a polycrystalline thin film, your X-ray diffraction pattern may not match with the polycrystalline X-ray diffraction standards. So you have to see whether it is having some textured growth. This is very important. And next one is sheet resistance. Okay, so we can measure the sheet resistance by this 4 probe, and then I can calculate what is the sheet resistance for my material. Why I am telling this one is, for a bulk material like a piece of copper which is very thick, I can use my formula as rho equals to RA by L. So R is the resistance, A is the area, L is the thickness, okay, or T, whatever it is. Okay, that will give me my rho. So if I take a linear 4 probe, what I will do, I will apply a current between the probes 1 and 4 and measure the voltage drop between the probes 2 and 4 on the surface of my copper. Okay, suppose this copper is, say for example, 2 mm thickness. 2 mm thickness is very thick, you can handle it very easily. Okay, and the probe spacing will be around 1 mm. Most of the time it will be around 1 mm, right? So if it is 1 mm, you see that the material thickness is much larger than the probe spacing. So it will have a different current path. Whereas in the case of thin films, we are dealing with a very, very thin film. Okay, substrate, the film will be of the order of say 100 nanometer. Okay, so 1 nanometer is 10 power minus 9 meter. Okay, so whereas the probe spacing which you are keeping to measure the resistance and all will be 1 millimeter. So 1 millimeter is much, much, much larger compared to 100 nanometer. In this case, you will see that the standard formula for measuring the sheet resistance or the resistivity will not be valid, because the current path taken in this particular case will be very different. So what I am supposed to do is I have to apply some correction factor. Those correction factors are given here depending upon the probe combination. So my sheet resistance will be having a formula F into V by I. So V is the voltage drop, I is the current. So generally in measurement, we will apply the current which is known, 1 milliampere, 2 milliampere. We are going to apply the current by using a source meter. So we know. We measure the voltage drop. So if you make V by I, you should get a resistance. But because of the current flowing in a different path for a very thin film, I have to apply a correction factor. Some theories are there. So based on that, they have given some correction factors here. Give this correction factor here and then calculate my sheet resistance. You remember the word, you see that I'm not telling resistance. I am telling sheet resistance because it is a thin film. So always you have to tell it is a sheet resistance. You know that the resistance for the unit for resistance is ohm, whereas here the sheet resistance is ohm per square. So most of the time it is given as ohm per square like this. Square in the sense for a square area. It can be 1 centimeter square, 2 centimeter square, 5 centimeter square like that. Okay, that's a notation here. So the resistivity will be your sheet resistance into thickness. You see that this formula is also changing here. So it's not a conventional material because the thickness is very small, of the order of dimensions of nanometer. You will see that the probe spacing is much larger. So the sheet resistance will be Rs into T. T is the film thickness, Rs is the sheet resistance. Okay, so this is very important. Then coming to the electromagnetic radiation. Okay, so up to this it is basics of thin film. Now I will little bit speed up and then I will tell you what is a transparent conducting electrode, and then I will give some of the results of my tantalum doped tin oxide. So you know that this is a familiar picture showing the visible radiation. So you will see that metals are all opaque. Copper, gold are all opaque because electromagnetic radiation cannot pass through this particular metal. They get just reflected off this particular metal because electrons are more in the case of your metals. So free carrier absorption will be there. All your incident electromagnetic radiation will be absorbed by the free carriers. Whereas when you come to a glass or a semiconductor with a wide band gap, you will see that they have sufficient band gap and less number of carriers. So obviously the electromagnetic radiation can pass through your particular glass medium or sometimes semiconductor medium. Okay, this is very important. Okay, with this idea, we will go into the concept. What is a transparent conducting oxide? Okay, so now you recall the touch screen of your device. Okay, whatever the mobile phone or touch screen laptop you are having, when you are touching, there is a signal carried. So how this signal is carried? That means there should be something happening there. Some change should be happening there. And you see that your screen will be divided into different locations. Okay, your click button will be appearing in different locations. The entire screen should have some sensor there. So that sensor should be conducting. Then only a signal will be carried. At the same time, it should also be transparent. Then only the light coming from your display device, LED or OLED kind of thing, will reach your eye. Okay, that is a very important part here. So the material which is on your screen should be both transparent and also conducting. Whereas by Maxwell's equation, you will see that metals are going to be opaque, and then glass will be actually highly resistant. So you cannot have both the functions in the same material. Okay, Maxwell equations limits that one. But there are a set of materials which can have these two contradicting properties coexisting in the same material. So those materials are called as transparent conducting oxides or transparent conducting electrodes. Okay, so to achieve these two properties in the same material, it's going to be little bit challenging. So you will see that these metals are called as TCOs. So what are all the properties or requirements for having a transparent conducting oxide? Say for example, the first one is called cadmium oxide, that was reported in 1907, okay, by a German physicist, Baedeker. So, but this is going to be toxic. Okay, cadmium oxide is very much toxic. So you cannot commercialize that one. It's a cancerous material. So people will go for non-toxic material because now we are using very widely all these TCOs. So when you see the resistivity, you will have will be of the order of 10 power minus 3 centimeter or less. Transmittance should be more than 80%. Otherwise, your display will not be very bright. And carrier concentration for conductivity should be of the order of 10 power 20 per centimeter cube. That means it should be of almost like a metal. Okay, metals have this much carrier concentration, but they are not transparent. Whereas your glass material will have high transparency, but their carrier concentration is very, 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 very low. Okay, that is the problem here. So we should look for a material which should have a very wide band gap so that I can improve the transparency. Also, I should have a higher conductivity. Now, let us see a classification of applications. Say, for example, if you want to use these transparent conducting oxides or electrodes for solar cell application, where there is a power trapping from the incident photons, I should have very low sheet resistance. So it will be of the order of 5 ohm per square. Or if I want to use it on a OLED, like OLED TVs and all, I should have around 200 to 100 ohm per square, depending upon the manufacturer. Likewise, if I want to use it for a touchscreen application, then the resistance can be slightly higher. It can be even up to 500 ohm per square. Okay, so in between smart windows and the LCD TVs come into picture. These are all some of the range of the sheet resistance which should have And these materials should have environmental stability, resistance, and very low electron function kind of things. Okay. Now, this is a picture which shows you the components of a touchscreen display. Okay. So this is taken from the web. So you can see here the touchscreens are of two types. So one can be resistive switching. Okay, resistive switching type. Another can be capacitive switching. Okay, capacitance based. Okay, so if it is a resistive switching, you can see here, one electrode will be at the bottom, one electrode will be at the top. So when you press it with a small amount of space, when you touch it, you will see that this electrode should go and touch the bottom electrode at that location, and then an electrical impulse conductivity will be taken to the processor. This is called as resistive switching. Most of the time, you will see that resistive switching is not that much widely used, because sometimes you have to apply a huge pressure and electrical conductivity has to go there. So that is not that much convenient. Whereas when you come for a capacitive switching, you can recall a capacitor, you will have two parallel electrodes, okay, with an insulator or a dielectric medium in between these two. So this capacitance of a material, of a capacitance, depends upon the distance d between the electrodes. So what we can do is, we can make a capacitive, touchscreen device where the bottom electrode and the top electrode, conducting electrode, will have a small amount of gap. So when you touch it, you will see that a small, variation in the distance will happen. This capacitance variation is enough to give a signal for your processor. So that gives a on signal or off signal. So your processor will be happening there. So this capacitive switching is what is most of the time used in your mobile phone touch screens. Okay. So obviously, one of the bottom electrode at least should be conducting. And below this one only, you are having all your LEDs. So light coming from your LED has to pass through several of these layers. Say it's an LED or LCD, whatever it is. So from here, light will be originated. It will tell to play the movie. The processor will tell to play the movie. So accordingly, current will be supplied to this LCD. And this LCD will be emitting light accordingly, blue, green, or yellow, whatever it is. And that light has to pass through several things, and then it has to reach your eye here. Okay, so that means all these layers should be very thin, otherwise absorption will be there. So your touch screen should be very much, very much stubborn, and also it should be highly transparent, and one of the layers should be highly conductive. So this is the challenge here. So you can see here, apart from this LCD, you will have other electronic components below this one. But you will see this layer screen itself is having several layers there. Okay, so this is the importance of your thin film and also the transparent conducting electrode. Now let us see what is the material generally people use in your touch screens. So that is called as indium tin oxide. It's shortly called as ITO. So it will have 90% of In2O3 indium oxide and then 10% of tin oxide. So this alloy will be useful to create a transparent conducting oxide. So this is one of the best available material on the earth. Okay, so all your mobile phone touch screens will be having this indium tin oxide. Okay, it's a transparent layer, and at the same time it is highly conducting. Okay, so this material, what is the problem with this material is, it is only available around 8 to 10% in the Earth's crust, and already we started using several of the deposits here. And again, this indium is not available in all the countries, only available in some specific countries. So obviously, it becomes very expensive here. Okay, so you can see here, not only that one, the problem here is recycling is the biggest problem. Okay, if you make a very thin nanometer sized coating onto your glass substrate, after your mobile phone is gone bad, if you throw it away, there is no means to collect it and remove this indium. People collect these mobile phones and then they go for the gold and other things. Okay, but not for indium. Indium recycling is very, 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 very limited, especially from display devices, because the adherence of indium tin oxide is very, very strong. So removing from the surface and doing chemical treatment and retrieving indium separately is going to be an expensive business. Okay, so people always go for some other alternate material to this indium tin oxide. So if you see this particular slides shown here, you see here mostly it is used for touchscreen related applications only. IT was used for touchscreen applications, and the need for touchscreen application, some 10 decades before was very, very less. Whereas in 2021, you see that the need is very high, and obviously the usage is very, very high, especially in this pandemic situation. Everybody is buying a mobile phone or a touchscreen display. So what happens here is, you see in 2017 also, ITO was used very dominantly. 2018 also, ITO was used very dominantly. Okay, this is a prediction only. And 2026 and 2027, you see that this blue color is alternate materials. Okay, because we cannot go on use ITO. After some, 1 or 2 decades, totally indium will be used off. We don't have indium in here. That is the biggest problem. So what I have to do is, I have to go for some alternate material to minimize the usage of ITO, okay, or to supplement the usage of ITO so that you can balance it and you can prolong it for some more time, or you can find some suitable alternatives. That is an important thing. Okay, so in 2026, 2027, you can see that almost nearly 30 to 40% of usage will be from alternate materials. So this is a very important point here you have to understand. Okay. Likewise, this is also another picture which shows which are all the places where indium is used. Say, for example, alloys, batteries, thermal materials, photovoltaics, soldering material. All these things you will use, indium. But you see the major part, 56% is used for only flat panel displays. And obviously, this number will be increasing now, especially in this pandemic situation. Okay. Whereas you see this material forecast here, how much is the tons of indium, supply and demand here. You see that this red color or pink color is demand, and what is the supply? In 2010, supply was more than demand. You see the prediction in 2020. You see that the demand is more than the supply. I think this data has to be revised because now in this pandemic situation, nobody expected this one. Obviously, this may be much more than the supply. And in forthcoming years, you will see that this demand will be very high, supply will be very, very low. So obviously, we are forced to look for alternate materials. So what are all the alternate materials which are available, in the literature? You see that there are too many materials are available here. I'm not going to touch all the things. Let me tell you only one material here: tin oxide. Okay, tin oxide is very cheap material, and it is an N-type material most of the time. And you have different dopants using which I can put into tin oxide. Okay, so if I have tin and oxygen here, I can substitute some part of tin with antimony or niobium or tantalum. So these niobium, tantalum, which I'm going to dope into tin side, will give free carriers, electrons to the system. So already SnO2 is a wide band gap semiconductor. So transparency is not a problem in tin oxide. Only thing is conductivity is a problem. So to improve the conductivity, what we can do is we can put some donors into the material. Like in the case of silicon, you are doping with donor elements. I can put some donors. So antimony, tantalum, niobium are actually donors into my tin oxide material. Okay. So now let me see how we can deposit the film. So there are several techniques. As I told you, physical rapid deposition, chemical rapid deposition, too many techniques are there. But I won't be touching all these things. I will take only one chemical method here, spray pyrolysis. Okay, so using this method, we have made some thin film. So you can see here, this spray pyrolysis shows you a mechanism here. So I will skip this mechanism for want of time. I will explain directly how it is done. Okay, so you can see here, say for example, if you take a perfume bottle, the simplest one is perfume bottle. You know that you use different kinds of perfume. When you press the perfume, you will see that a lot of advertisements are coming, fog is happening, kind of things. So that means you will see that very fine aerosols will be emitted from your perfume bottle, aerosols. So aerosols are a kind of mixture of gas and fine particles. So whatever material you are going to come out as an aerosol, this is a very, very fine, small droplets. What you do, you put a heated substrate here. You put a heater here, put a glass piece there at a high temperature, say for example, say 300 degrees centigrade, say for example. You use a perfume bottle, take your tin chloride, SnCl2, say for example. You spray it. So along with the air molecules, your SnCl2 will be sprayed onto this one. The moment it is very, very fine droplets, you will see that this temperature will disintegrate this chemical, and then it forms SnO2. That's called as pyrolysis. Pyro means temperature. So when it pyrolysis, you will see that this tin chloride will be, disintegrated. Chlorine will be removed as a gas. It goes outside, and then tin, along with air or oxygen in the air, will form SnO2 layer onto the substrate. This is the simplest spray pyrolysis which we can tell you. Okay, and people have done good work using simple sprayer itself and published papers. Okay, but control will be very difficult. So we go for this spray pyrolysis unit. Same thing is shown here. We will have a solution here. I will have a double walled gun like this. This is a spray gun. So through the inner gun, I will put the solution. Through the outer gun, I am going to put gas or air, compressed air. So due to this end is tapered, okay, this tip is going to be very much tapered with a double gun. So due to Bernoulli's principle, you will see that there is going to be a lot of pressure difference and you will create aerosol coming out of the system. So this aerosol will be projected onto the heated substrate and then it will be dissociating into oxide molecules and forms as an oxide layer here. And the extruded gas, I can put the exhaust and then I can pump it out slowly. Okay, so these are all the controls to on and off for the system. So this is called as spray pyrolysis unit. Okay, so using this technique, we have prepared a tantalum doped tin oxide. So now we come to the material. That is a method. Now we come to the material. So when I put tantalum here, you see that tantalum mostly it stays in a 5+ charge state. Whereas when I take SnO2, Sn will be in 4+ charge state because oxygen will have 2-. There are 2 units of oxygen, so it will be 4-. So 4-, Sn should be in 4+ state. When I put tantalum in 5+ charge state, okay, when I put tantalum oxide here, what happens is tantalum will use 4 electrons to bind with oxygen, and 1 electron will be left free. This electron will be donated to the lattice, and we can improve the conductivity of tin oxide. Okay, so what we are doing in this work is we are putting different concentration of tantalum into tin oxide, and then we are trying to see which combination is best for our transparent conducting oxide application. And then we also tested this one as a counter electrode for making a solar cell. Okay, so now I will slightly speed up. I won't go much details of the data because time is also limited. So this is the unit which I showed you. All those things are in this region inside this cabinet, and I will have my heater here. This is the heater, and my substrate I will put it here, and my gun will be somewhere here. You see that the height between the gun and the substrate is very, very important. Okay, I will project here once again this table here. You can see these are all the control parameters which are associated with the spray pyrolysis technique. The starting material is important because it should have a low decomposition point, and solvent which you are putting is also very important. And then the substrate which you are using, substrate temperature, carrier gas, pressure of the gas at which you are using to create vapors or the aerosol of this particular solution. And then when I spray this solution along with the compressed gas here, you will see that this solution along with the compressed gas will cool this substrate. Say for example, when I keep 400 degrees centigrade, when I spray once, temperature will come to almost 325 degrees centigrade. So what I have to do is, I have to have an idea about the distance and the pressure and this cooling temperature and all. Because I have to spray this aerosol so that it should reach the temperature where its decomposition point should be satisfied. Okay, if the cooling is too much, if it goes to 200 degrees centigrade, nothing will happen because your tin chloride material needs nearly 300 degrees centigrade for decomposition and forming a film. The temperature is cooled off to 200 degrees centigrade, it will not decompose. So you won't have tin oxide material there. Instead of that, you will simply have tin chloride only sprayed onto the substrate. So this cooling effect has to be taken care. And not only that one, I cannot spray it continuously. If I spray continuously, what will happen? Okay, the temperature will come to 100 degrees centigrade and nothing will happen there. Okay, so what I have to do is, I have to spray for a moment and then I have to wait for some time, like 30 seconds to 1 minute. So the temperature has to come back to 400 degrees centigrade. Only then I can maintain the decomposition temperature for tin oxide. Okay, that is the condition which is given here. Okay, so I will be spraying for 0.5 seconds. Just a moment only I will spray. That aerosol will come to the substrate and then that itself will cool my substrate nearly 75 degrees to 100 degrees centigrade. So I have to wait for 30 seconds for the heater to supply heat and to regain the temperature. Okay, then only I can maintain the temperature, suitable for my decomposition. So this is the conditions. Then coming to the X-ray diffraction. So now you recall the X-ray diffraction which I told you. So now we have estimated the texture coefficient for my pattern of this set of thin films for pure tin oxide, and then 1%, 2%, 3, 4, 5% tantalum dope. And then we have estimated the texture coefficient, and you see that the texture coefficient is higher for 210 direction. Okay, so that means the particles on the surface of my film are already oriented along a particular direction. Why? Because this particular direction orientation is called as anisotropy. Okay, it's called as anisotropy. So this is a directional dependent property. The electrical property, optical properties are all dependent upon the direction of the crystallographic direction of a material. So if I have a better property along this direction, then I can adjust the parameters, try to grow only along this particular direction. So that is why measuring of this texture coefficient is very important, apart from identifying the phase formation, because I want to have only SnO2. Sometimes if my preparation condition is not good, it may form SnO, which is an unstable phase sometimes. I don't want this one, I want only this one. So to confirm the phase, they have to make the X-ray diffraction, also to sense for the texture coefficient. And then we used an X-ray photoelectron spectroscopy to identify the charge state. So this shows that tantalum is eventually in a 5+ charge state. Okay, so obviously it is going to be conducting. So then we did some scanning electron microscope to see the surface morphology. So usually the surface morphology of tin oxide will be having a kind of tetragonal structure. Okay, tin oxide is actually having a tetragonal structure. So here you can see that it's almost kind of tetragonal. The shape is nearly a tetragonal structure of the particle there. And also we can do the compositional analysis by EDX, energy dispersive X-ray analysis, called as EDX. And this will be giving you the presence of tantalum. So you can see that tantalum is also present in the film. Because it's a spray pyrolysis, if you don't maintain the preparation parameters properly, sometimes these vapors will be going out of the system. It may not even fall on the substrate sometimes. So the tantalum content may not be even there inside the film to the expected level. So it is important to identify whether the percentage of tantalum is there or not. Then coming to the optical properties. So in the optical properties, you will see that the transmittance is measured as a function of wavelength for all the films. So you see that the transmittance is as more than 80% for the visible region. So this is a visible region. So here you'll see that the transparency is more than 80%. You can see the photographs shown inside. These are all transparent glass slides over which this material is coated. And then we can use a formula to estimate the band gap. That's called as a tau relation. And using tau relation, we can calculate the band gap of the material, how the band gap is going to vary as a function of dopant concentration. Okay, and then we can measure the sheet resistance and resistivity using the using the formula which I told you. We can measure the sheet resistance. Also, we can use Hall effect. Okay, in your school days or even in your first year BTech, you might be studying about Hall effect. And then we can measure the carrier concentration, type, and mobility, all those things. So you'll see that as a function of tantalum concentration, which is the best film. So you see that sheet resistance here along y-axis is shown here. Pure tin oxide, you can see that it is more than 1000 ohm per square. That means it is not that much conducting. In fact, normal ITOs will have just 10 ohm per square. A good quality ITO will have 10 ohm per square. Whereas the pure tin oxide, which is given by symbol TO, is very high. So this is not going to be useful. Okay. The moment I dope tantalum, you see here, it comes to around nearly 200 ohm per square. So tantalum doping is actually reducing the resistance of the material. So when I keep on increasing the content of tantalum, you see that it's almost coming to nearly to 20 ohm per square. So for 4% of tantalum, the resistance is very low and resistivity also is very low. You see the carrier concentration for the same material composition. You see that this carrier concentration also very high and mobility is also very high for that particular 4%. So this is going to be a good system for as an alternative material to indium tin oxide. So this is the table which shows you all the optoelectronic parameters like band gap, roughness of the film, thickness, carrier concentration, mobility, resistivity, sheet resistance, and this is activation energy for conduction, and then the surface work function. So if you see for all the films, this is for pure tin oxide, 1% tantalum, 2%, 3%, 4%, 5%. You see that this 4% is going to have a much better property compared to other concentrations. Okay, so we can further explore this 4% tantalum doped material for our alternative TCOs. You can see here the sheet resistance is around 18 ohm per square. Okay, so we round it off, it will be 18 ohm per square. 18 ohm per square is really good. Okay, and whereas that surface work function is not as good as your indium tin oxide. Indium tin oxide is the best one. If this tantalum doped tin oxide, I cannot claim it as a complete substitute for ITO. But in the range which we can use it for different applications depending upon the sheet resistance, we can try to use these alternate materials and we can try to reduce the quantity of ITO used in the market. You can use it ITO only for essential purposes where it is really needed. Otherwise, in some other applications, I can use these alternate materials. I can try to supplement this particular use. Now, we also made a large area deposit, 10 centimeter by 10 centimeter, and then we measured the sheet resistance. And remember here, when I make an aerosol for deposition, it goes like a cone, inverted cone. So when I keep my substrate here, there is no guarantee that entire substrate will be uniformly, sprayed. So always there will be some variations, and temperature gradient also will be there. So you see that when I make a large area, only the center part is good. Center part is around 18 to 19 ohm here. This color coding you can see here. Violet color is at the center. When I go to the edge, you see dark blue. Dark blue color is around 55 to 62 ohm. So the sheet resistance is good only in the near center part of the 10 by 10 centimeter. At the edges and all, it is going to vary. So we have to overcome these issues. Okay. And then we also tested this particular temperature stability as a function of annealing duration and temperature. So when I increase the temperature from 200 degree to 450 degrees centigrade for about half an hour or 1 hour, and then we measure the sheet resistance once again. You see that as a function of temperature, sheet resistance is decreasing up to 400 degrees centigrade. When I give you a temperature more than 450 degrees centigrade after deposition, you see that sheet resistance is increasing in all the cases. Likewise, when you do an annealing processing, more than half an hour, you see that the temperature is going to, the sheet resistance is going to not to be that much favorable here. So what I have to do is, sheet resistance is increasing with the duration. You can see here half an hour, 1 hour, 1.5 hour, 2 hour. You see the sheet resistance value is going to 80 ohm per square. Whereas when I do it for half an hour, it's only around 30 ohm. Because the sheet resistance of TCO material increases with temperature beyond a particular value. Because we'll be using these electrodes for making some solar cell device like this. So this is a dye sensitized, solar cell here, DSSC, called as DSSC. So this is the mechanism. Here we will use usually 2 electrodes here. Most of the time they will use for DSSC fluorine doped tin oxide. That is another TCO material. Or if it is a polymer solar cell, people will use indium tin oxide also. So to supplement this material, instead of this ITO or FTO, I can put my TTO here. When I put my TTO there and measure fabricated device, and then I have to do a lot of intermediate steps for annealing, for sandwiching all these intermediate layers. At that time, my property should not come down. So that is why we are making the temperature stability here, and we are studying and having an idea here. Okay. So when I come to the efficiency of my device, so this is a device which we fabricated, and after doing this one, you can see that what is the efficiency of this device. So here you can see that when I use a standard fluorine doped tin oxide, that is a commercially available material as an electrode, you can see here the efficiency is 5.5% power conversion efficiency. For my TTO, it is showing 3.26. So obviously it is less than the standard one, but still, as an alternate material which is explored for in a lesser impact, you can see that this efficiency is not very bad at all, because it's 5.5 by for standard, it's coming to 3.25. So if you alter all several other parameters, you can definitely improve the efficiency of this TTO. So these values prove that TCOs has transmittance around 86%, which is good for a TCO. Also the sheet resistance is also very good, and this is for a particular green color wavelength, which is an average wavelength for visible radiation. It is good, and temperature stability is also 400 degrees centigrade. Whereas your FTO will have a temperature stability around 500 degrees centigrade. But because of this one only, you are having a higher efficiency there, because the layers will be formed properly when you make a device. Whereas the annealing temperature is lesser for this particular sample. So we have to see how we can improve this temperature stability so that it can be on par with commercially available FTO. And DSSC is showing 3.26% efficiency, and the surface work function is 5.08 electron volt. This is not as good as ITO, because nothing can match ITO, but still it is not bad. It is, really an appreciable value for device applications. Okay, so with this I conclude, and thank you for listening.
Thank you very much, sir.
So thank you very much, sir. Very nice presentation, Dr. Paul, sir.
Yes, sir. Any questions, sir? I'll be happy.
Yeah, questions. Before that, just I wanted to make a few comments about your thing. In fact, I have gone to my olden days when I took thin film technology and eye vacuum technology at PSG College of Technology.
Okay.
83 to 85 as selective. At the time, K.L. Chopra book and the handbook of thin film technology.
Yes. I read that book.
Yeah. So that in fact, I have gone to that because the way in which you presented the things, you started from the definition of the thin film, and from that, what are the various parameters, how preparation of the thin films, what are the applications. Really, it is superb, sir, hilarious, and very fantastic. And I hope all our participants would have benefited, especially the people who are planning to do research in thin film area, because she said most of the people, they are working on powders, nano powders, but nano composites also, but thin films not much, because they have to start from the basic eye vacuum technology, and then from that heat resistance properties studies, and then as you told, it is in terms of micrometers. The characterization also was very fantastic. In fact, I can say that this type of lecture really, I enjoyed it. In fact, basically,
Yes, thank you.
Sir.
In fact, K.L. Chopra book and all, at the time we read, and thin film handbook. It was very wonderful book.
Yes, sir. I also cited papers several times. K.L. Chopra and Shanti. Student cited their papers very clearly.
In fact, he was the IIT Kharagpur director also for some time. IIT Delhi also he was there. And really, it was a very nice, and I got an opportunity to meet him in IIT Madras when I was a research also. Really, it was a wonderful combination of all the things he have put. So, all the best, and continue your research. And I think a lot of application oriented, because people are talking about the mobile phone, e-vehicles, and all, even e-vehicles. Now the people problem is the battery. Even for that, how best we can give that type of things, nano sensors. Lot of work is going on nano thin film. In fact, you told about the connecting polymers also. It was also a wonderful, good area for the research also, the people who wanted to do. So really, thank you very much for your.
Thank you very much.
In fact, I am very much impressed by your presentation, sir. So now we will go to the question session, sir.
Yes, sir.
Please, please ask.
Thank you, sir. Thank you, sir. Now the session for question. If you have any clarification, you can interact with the speaker, sir. Any participant, if you have any questions, you can interact, sir.
Paul Joseph. Hello. I am Dr. Tilak Kumar. Paul.
Sir, how are you, sir?
Thank you, sir.
Very nice and excellent presentation, Paul.
Thank you, sir.
Okay, then what type of glass material will be used for growing that thin film?
Sir, usually we will use sodium silicate, sir. But the problem in sodium silicate is when you go for higher temperature, the sodium from the glass will go into your film. So to avoid that problem, we will go for Corning glass. Corning glass is slightly expensive, but we can go for Corning glass.
Is it available in Sigma Aldrich?
Sigma Aldrich, it will be expensive, sir. You can go for other companies also. Contact a local supplier. Sigma Aldrich will be very expensive, but that is available, sir. In other companies also, it is available, sir.
Very nice. Thank you. Then we are trying to do that by using spray pyrolysis. We are having an instrument with a double gun, either in the forward direction as well as in the reverse direction. It will coating.
Yeah, you can raster that one up and down in X and Y directions.
Thank you, Paul. Excellent presentation.
Thank you, sir. Thank you,
Congratulations.
sir.
Thank
For a
you,
long
sir.
time I'm talking to you.
Yes.
We also discuss on the day of discussion, sir. Thank you, sir.
Thank you.
Any
Sir
other
was
participant?
taking physics for me in my BSc in
Yes,
Karloor Synthesis.
yes, sir.
Sir,
Any
hello, sir.
participants? No, yes, sir.
Hello, sir. Hello,
Yes,
Hello.
sir.
hello.
Yes, sir, you're audible, sir. Audible, sir. Hello.
Yeah, this is Arjun from Bharadasan University.
Yes, sir. Yes.
So I got one small question. So how to differentiate the composite as well as dopant?
Composite means it will be coexisting, and the ratio of elements in the composite will be very high, actually.
Okay,
Whereas dopant means it will be in a small quantities, and they go and substitute the cationic site or anionic site. That is called as dopant, and the dopant will not change the crystallographic structure. And most of the time, composites will be two independent crystallographic structures. They will materials. They will mix together. They will just coexist side by side. That is what we can call it as a composite. But what we are doing here is a dopant action. It just replaces the atoms, tin atoms, with tantalum. That is called as dopant.
okay. Sir. Thank you so much, sir. Really nice lecture, sir.
Yeah, thank you.
Thank you, sir.
Excuse me, sir.
Yes, madam, please.
Good evening, sir. I'm a student.
Yeah.
Sir, I want to ask a question. Can I?
Yes, please.
Yes.
Sir, in the upcoming years, we're gonna use alternative mostly. So, in the alternative, is alternative for ITO is as effective as using ITO?
As effective as?
Not clear.
ITO, sir.
No. Can you come again?
Indium tin oxide. Yes,
Actually,
sir. My
as I
question.
told you, to my knowledge, there is no material, on par with ITO. Very recently, aluminum doped zinc oxide has picked up. That is also a good alternative material, and people have started commercializing also. But the performance of ITO is very excellent. Okay, so that's why I'm telling you, if you really want to have, say, for example, an electronic device kind of thing, then you can go for ITOs. Suppose you want to put in a film for window heater. Say, for example, in cold countries, you will have a lot of snowfall. You want to heat the window. For that kind of thing, at the same time, you want to have light passing through the window. Those cases, you need not use an indium tin oxide. It's not going to serve that much better, that much work. So it is going to be a crude kind of application. So there I can use these supplement materials. So that way we can save the indium for the best applications only. That's why I told that it's only a supplement. It cannot be a replacement for indium tin oxide.
Sir,
Thank you very much, sir.
Thank you.
sir,
Hello,
I'm
sir.
Abid, sir.
Sir,
Please.
sir, how to
Sir,
confirm the
can I-
stable phase of SNO2 or SNO? How to confirm?
Generally, we do X-ray diffraction, but as I told you, in the X-ray diffraction for thin films, you will have a textured growth. So, because of this textured growth, you cannot identify by matching it with the JCPDS file, because many of the peaks will be absent in your thin films. So, what you are supposed to do is,
Okay.
you can go for a Raman measurement. Raman is surface sensitive. That will give a different modes for SNO2 or SNO. From that one, you can identify what are the modes that are prescribed for SNO2 that should appear here. And what are the modes that are appearing for SNO that should appear separately. So if you have mostly the modes corresponding to SNO2, then you can identify, okay, this is the phase form. That is an additional confirmation. X-ray can tell you, but especially it is a thin film form, all the peaks may not be appearing there. So you will get in confusion. Really, it is a this phase or other phase. Okay, that is the biggest problem. So you have to supplement that data along with your Raman also.
Okay, sir. Thank you.
Yeah, thank you.
Any other
Sir?
question? Yes.
Yes.
Sir, I'm Abid, sir.
Yeah,
Student,
please.
sir.
Yeah.
Sir, how to get good coating of reduced graphene oxide on a glass substrate, sir?
RGO, by which technique you are coating? That is important. Which technique you are using? Any idea on that?
No, sir.
Say, for example, if you are going to purchase commercially RGO, it's available actually in Sigma Aldrich. If you have an RGO, if you are going by spin coating, Okay, because already you have formed RGO, it is a suspension. So better to go for spin coating. In spin coating, you can adjust the viscosity and you can try to coat an reduced graphene oxide layer. Because in spray pyrolysis, you are going to waste a lot amount of material. RGO is very expensive. You cannot spray an RGO. You are going to have a lot of wastage. Okay? Instead of that one, if you go for a spin coating, you can just drop it. It's just basically a drop casting. You'll put a viscous, drop of RGO salt onto a rotating substrate. So you just put a drop there, it will be just spinning. So hardly you will be wasting only 2 or 3 drops there. That way you can save the material and still you can get a good quality. But there only main thing is you have to take care of the RPM, rotations per minute, at which speed you are rotating your spin coater, and also what is the viscosity of your solution, okay, or concentration of RGO. So this is an important parameter to get a good quality RGO film by spin coating.
Okay, sir. Thank you, sir.
Thank you.
Participants, any other questions?
Excuse me, sir. I'm Lakshmi from Srm Vec.
Yes.
Can I
Yes.
ask a question?
Yes.
As thin film has so much of applications, and how it is used in wireless communication and telecommunication, sir, rather than transmission and reflection, how it is mostly used, sir, thin film in wireless communication and telecommunication, sir.
Thin films in wireless and telecommunications, actually, I am not aware how they are used directly. Say, as you say that, they can be used as a waveguide, but again, that involves, reflection only. You have to take care of the skin depth of your material. But mostly, these kind of thin films may not be useful. Transparent grating electrodes may not be useful as a waveguide, because waveguide you have to have a lot of reflections. This will allow the light to pass through. So obviously, you have to go for a metallic thin films. Okay, you can take an aluminum or you can take copper and make a thin layer of that material and make a waveguide. Then you can allow the electromagnetic radiation to pass through. Again, there you have to take care of the thickness, because Maxwell's equations tells you about the skin depth. Though metals are opaque, if you keep on reducing the film thickness below a particular limit called as a skin depth, then even metals are partially transparent. So when you make a thin film waveguide, you have to take care of the thickness. You should not be making it more thin. You should make it an optimal thickness so that the light will be reflected rather than transmitted. So directly, we may not be using it except for this waveguide. Otherwise, you will make a lot of electronic devices which are actually involving thin films only in their fabrication. All our ICs, chips, motherboards, they have all this thin film evaporation technique only. If you go for chip manufacturer, you will see this one. They have complete clean room facilities. All these evaporation facilities, high-end evaporation facilities will be there. So all your ICs and chips and millions and millions of transistors are made by thin film technology only. So IC technology, encompasses thin film technology. So without this thin film deposition techniques, your IC technology cannot survive. This is the fundamental for that. That way, it will be supplementing. It will be contributing, not directly. Any other questions?
Sir, I'm Anbucharian coordinator, sir.
Sir,
generally in thin film or any composite nanomaterial, why the N-type materials are chosen? Why N-type layers are used for coating?
This is a good question, sir. Because getting a P-type material is not so easy, sir. Say, for example, if you take silicon, it is easy for silicon to be doped into N-type and P-type because we know that. But the problem with indium tin oxide or oxide-based material is most of the time they will have oxygen vacancies because basically it's SnO2. If it is completely stoichiometric, it will be an insulator actually, or at least wide band gap semiconductor with very, very low conductivity. But the conduction mechanism for all these oxide systems is several of the oxygen molecules will be missing. Once the oxygen molecules are missing, you won't have an oxygen there for the tin element to form a bonding. So it doesn't know what to do with the two electrons. So what it will do, obviously, it release it in the matrix. So that serves as a free carry. So by default, non-stoichiometric or oxygen vacancies present in your tin oxide or most of the oxide system will be acting as a donors. So that is a problem there. Apart from you dope it, eventually, it is naturally a kind of N-type material. with respect to defects present in the system. So if you at all you want to make it into p-type, you have to compensate for all these defects, and then you have to put a suitable acceptor dopant there. That is going to be complicated. So that is why people are not going for p-type material. There are reports like, say for example, dioxide CuAlO2 materials are there, but again it is a multi-component system. CuAlO2 means it's complicated structure. Again, making it as a stable material is once again complicated. That is the reason people are, most of the time exploring N-type material. The P-type material is really challenging. But if you could make a stable P-type material, then you can have, you can realize see-through electronics. People have done that and demonstrated on a small scale. Okay? You can have a see-through electronics because both the host materials, N-type and P-type, will be of the same material. So it will be having transparency, and you can make a see-through transistor, see-through electronics can be completely made. So that is one of the advantages.
Yes, sir. Thank you very much, sir. Thank you, sir. Participants, any?
Excuse me, sir. One participant posted a question in chat box. Her name is Dhanalakshmi B. How to identify whether an added element exists as a dopant in our sample or as a reinforcing element within bracket composite? How to confirm this through with study?
Yes, sir. Actually, the presence of that element can be identified by EDAX. I told you that energy dispersive X-ray analysis. So that is a technique which will tell you what is the composition there. Or indirectly, you can also estimate it by the XPS technique. If that particular ionization peak is there, then we can confirm this is the element which is present there. In fact, from EDAX, if that element is present, you will have an energy peak corresponding to that particular element. And from the ratio of the intensities, we can tell how much it is present there. Okay, that is one point there. Whereas it is present, but whether it is present as a composite, like outside the lattice or into the lattice site, means that you have to do it by only X-ray diffraction, and then you can combine X-ray diffraction along with Raman spectroscopy and even XPS. For example, if it is going to be substituted at the thin site, it will have a energy peak in one particular value. Instead of that one, suppose if it is coexisting, that is, it's not in the site, it is just lying outside beams, then it will have a different binding energy there. So from the binding energy value position, we can tell whether this element is actually substituted or lying outside the matrix. That is one way. Likewise, you can supplement that one with Raman also to some extent. Again, from our X-ray also you can do. You have to do a very good quality X-ray. From that X-ray, you can tell whether you are having a substitution there or not. If it is substituted, you should have only the phases corresponding to the parent compound, that is tin oxide. If it is not substituted, if it is lying outside as a tantalum pentoxide, tantalum oxide, then you will get peaks corresponding to tantalum oxide separately in the same pattern. That means it is an impurity phase there. So that way you can tell whether it is substituted or it is segregated as small particles outside the lattice. Okay, so this is the techniques. These are the techniques.
Yes, sir. Thank you, sir. One more question, sir. Actually, sir. Actually, you spoke about that touch screen of laptop or mobile phones. You know that, sir. Sometimes the touch screen is not properly working, sir. That may be due to lifetime of touch screen or due to some sensitiveness of that touch screen, sir.
Say, for example, they will have a small gap between the top layer and the bottom layer.
Yes,
so
sir.
if you are, most of the time you will be putting your mobile phones down accidentally. If it falls down, sometimes the impact may go and affect the pixels and get broken. That may be the reason. Otherwise, if you keep it safely, I don't think it will be a problem. Because scratching is not a problem. Above these layers, you have a lot of protective layers. Scratching is not a problem. Once the mobile phone falls down, that impact will affect the the interconnects at which your touch points, sensitive points are there. That is the problem, I guess.
Yes, sir. But there is a lifetime also, sir. Each and every touch screen has its own lifetime.
Touch screen may be
number
having
number of cycles.
I don't think so. Because your ITO layer is concealed below the protective layer. Just by touching your ITO property may not be degraded. But your LCDs and LEDs below that will have some lifetime. Because if it is going to act only as a transmittance layer and a conducting layer, and these currents which are involved are very, very small. I don't think your material will be degraded. It may be not working due to other functionalities. As a material, just by touching, because you are not directly touching the material there.
Yes.
Okay, you are touching only the protective screen, diamond-like carbon films on the surface.
Yes,
that will pick up the pressure and all. So
yes.
I don't think that is the main issue. That is my opinion.
Thank you, sir.
Okay.
Thank you very much.
Sir. Thank you, sir.
Thank you very much, sir, for your wonderful presentation, sir. Now I request, is there any question? Can we go to the next
Sir,
part?
we can conclude, sir. We can conclude. Almost the time is 7:40.
Okay, sir. Thank you very much, sir. Thank you.
Thank you, sir. Thank you very much.
Sir, kindly wait, sir. There is a formality for vote of thanks, sir. By given another coordinator, I request Dr. Gandhimadi give the vote of thanks for the today event. Thank you.
Thank you, sir. Thank you, sir. Gratitude opens the door to the power, the wisdom, the creativity of the universe. I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. I thank our guest speaker, Dr. D. Pal Joseph, for readily accepting our invitation and the informative session. We had a very wonderful and informative session, and we have learned about the nanofilms from the growth to the application. Thank you so much, sir. I express my gratitude to our management, principal sir, vice principal sir, for giving us the opportunity to conduct these kind of events every month. I thank head HOD, heads of various departments, faculty members from our college and other colleges, and the research scholars. Last but not the least, I thank our students to make this occasion a grand success. Thank you so much. Thank you, one and all.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you, madam, very much for the opportunity.
Thank you, sir.
Kindly wait, sir.
Sir,
Dr. Paul Joseph, sir, kindly wait, sir. We can take one photograph, sir, with you. Now the sessions are
please,
over.
all of
Thank you, all the participants. Thank you, all participants from our college or other colleges. Thank you, my dear students from our college and other colleges. Thank you, one and all present here. So kindly wait for 1 minute, sir.
Sure.
I request our faculty members to turn on the video for the photo session.
So they are our faculty department faculty members, sir.
Padmaja ma'am.
Very nice to see you.
Nitya ma'am.
Yes, ma'am. Yes, ma'am.
Our head of the department and other faculty members. Thank you, all faculty members.
Thank you, sir. Thank you. Thank you, Paul, sir. Nice presentation, sir.
Thanks.
Thank you, sir.
Thank you, sir. Thank you very much. Really, very wonderful. So once this corona, everything is over, we will invite you for a real lecture.
Sure, sir.
Really, it was very nice. Or even when you come to Chennai, this side, I think maybe you are a native of Kadalur, right?
Yes, sir.
No, I am native of Pondicherry.
Pondicherry.
So next time when you go there, come this side, you please inform us. We will contact you. And
Sure. Recently, actually, I came back here. Very recently,
Yes.
I came back. But still, next time I will see, sir. Definitely.
Yes, sir. Possible, I will invite, sir, because one of our students, Sasrega, is doing the research in sir. Sasrega, ma'am, you can interact. Ma'am.
Yes. Sir, good evening, sir.
Yeah, good evening, madam.
Yeah, I have done my MPhil in thin films, sir. Zinc oxide in RF sputtering technique.
RF sputtering technique.
And I wish to continue the same in my PhD also. Concentrating on CIGS thin films for solar cell applications.
Okay. Copper and gallium.
I'm doing my coursework this year. Probably I'll get your guidance, sir. I want your guidance.
Sure. You can give me.
Yes, thank you.
Where is Nitya Balaji, ma'am?
Sir, she is having some network issues.
Sir.
She is going to submit thesis shortly to Anna University, sir. Nitya Balaji, ma'am.
Okay.
Yes. Dr. Badmuja from PSG College of Technology, sir. Soumya from Anna University, sir. Anjumani madam now recently last year completed the PhD, sir. Ramya madam is doing PhD in University of Madras, and Mrs. Pravina is also doing PhD under our HOD guidance, sir, and shortly going to submit the synopsis. And Dr. Tripadi from Annamala University, sir. So they are all our faculty members, sir.
Great.
Thank you.
Very nice meeting you, sir.
Madam, photo எடுத்துட்டீங்களா? நித்யா ma'am.
எடுத்தாச்சு சார்.
Yes,
Photo
yes, sir,
எடுத்தாச்சு
yes,
sir.
sir. I
நித்யா
also
madam
taken, sir.
இருக்காங்க. நித்யா
எடுத்துட்டேன்
ma'am.
சார்.
Nithya ma'am
she's
not yet
having
joined,
some
sir. No
net
problem.
issues, sir.
She is a coordinator for first year, sir. We will
Okay.
wait.
Sir,
Thank you,
message
sir.
பண்ணிருக்காங்க.
Thanks
net issues.
to thanks also to FICC is giving the permission to student or attend. Thanks also given, ma'am. You informed to coordinators also. First year
Yes.
coordinator and
Sure, sir. Sure.
FICC and thank you.
Sure.
We can conclude, sir. Or we
Ah,
will
yes, sir.
Yes,
Yes, sir.
Thank you
so
very much,
much.
sir.
Thank you.
You
Thank
had
you.
a very wonderful
We will
evening.
contact
Thank
you,
you,
sir.
sir.
We will contact you.
Ah,
Sir.
sure, sir. Sure.
Thank you,
Really.
head of the department, sir, and all our faculty members for wonderful support. Thank you.
Thank you,
Thank
sir. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you,
Thank you, sir.
Thank you, sir.
Sir,
Thank
all
you.
the people have put a feedback or we have to wait?
Yes, sir. Madam is checking.
Yeah, sir. I'll check.
Pravina, ma'am. உங்க ஸ்கிரீனே ஒரு மாதிரி இருக்குது. ஏன் ma'am?
நீங்க அப்ப செஞ்ச சூப்பர் கண்டக்டர் அப்ப சார் இப்ப செய்யறாரு சார் ரிசர்ச்.
அதுலதான் பிடிஎஃப் பண்ணியிருக்கிறாரு.
அதான் YBCO போட்டிருந்தாரு இட்ரியம் பேரியம் ப்ராப்ளம்.
ஆமா, எஸ் சார், எஸ் சார், எஸ் சார். நியூ டைம் கூட இப்ப
சார்
மேம்
173 ரெஸ்பான்ஸ் இருக்கு.
ஓகே மேம். நோ இஷ்யூஸ். ஓகே மேம்.
ஆக்சுவலா 199 வந்தது மேடம். ஒரு
203 மேக்ஸிமம் இருந்தாங்க சார். 203 மேக்ஸிமம் சார்.
ஓகே சார், நோ ப்ராப்ளம்.
பார்ட்டிசிபென்ட்ஸ் டவுன்லோட் பண்ணிருக்கேன் சார். 203 மேக்ஸிமம் வந்துச்சு.
Sometime
I have taken that photo also already sent to it, sir. 203.
சார் இது நல்லா பண்ணார் சார். நல்லா என்சைக்ளோபீடியா மாதிரி
எல்லாத்தையுமே கவர் பண்ணிட்டார்.
டெக்னாலஜின்னு இன்ஃபேக்ட் மேடத்தோட கைடு தான் எனக்கு எடுத்தாரு. ஜெயக்குமார் தான் எடுத்தாரு. அப்புறம் தங்கவேல்னு ஒருத்தர் இருந்தாரு அவரு. அப்புறம் நாயர் ஒருத்தர், சசிதர நாயர், அவரும் மேடத்துக்கு தெரியும். பத்மஜா
க்ளோஸ் பண்ணிடலாம் சார். தேங்க் யூ.
க்ளோஸ் பண்ணிடலாம் சார். 173 ரெஸ்பான்ஸ்
180 people ஸ்டாண்டர்டா அப்படியே இருந்தாங்க மேம்.
இருந்தாங்க சார். 180 கடைசி வரைக்கும் இருந்தாங்க சார்.
185 183 வரைக்கும் இருந்தாங்க.
ஆமா சார். ஸ்டூடண்ட்ஸ் தான் ஃபைனலா கொஞ்சம் முடிஞ்சோனே.
எனக்கு அந்த போட்டோவும்
அனுப்பிச்சிரேன் சார். அனுப்பிச்சிரேன் சார்.
Thank you very much, sir. Thank you.
Okay, sir. We'll end the session. Thank you, sir.
Thank you.
Thank you, sir.
Thank you, ma'am, for your wonderful support. Thank you, ma'am.
Thank you, sir.